So today I'd like to talk to you about quantum tunneling. And so what we're going to discuss is the simplest possible potential to set up with this originally, and that's quantum tunneling through a square barrier. Now what we have here is a potential energy function that has a constant value over some length L and is zero otherwise, all right? And we're also dealing with a quantum particle that has less energy than the energy of the potential barrier. So this is called a square barrier solution, and then whatever constant that barrier height is, that's our barrier height, okay? Now let's discuss what would happen classically for this situation. If you have some barrier height V naught, and the energy of the particle is less than V naught, then classically the particle would only be reflected. But the quantum mechanical result is one of the most remarkable features of modern physics, and there's a lot of experimental proof that it's true. What it tells us is that there's a small but finite probability that the particle will move through the barrier and emerge on the other side. So according to quantum mechanics, all regions here, if we start the particle at x less than 0, the barrier starts at 0 and runs to x equal to L, and then we look at what the probability is that the particle is in any of these three regions, x less than 0, between 0 and L, or x greater than L, all regions are accessible to the particle, okay? So the probability may be low that the particle tunnels through the other side, but it's not necessarily 0. Now what that would mean is that conservation of energy would have to be violated for a little bit. But remember, according to the energy time uncertainty principle, the particle can be inside that barrier as long as the time that it spends inside the barrier is less than the amount of time as dictated by the uncertainty principle. So if you look at what the solution to the quantum mechanical equation for this is, then the curve represented in this diagram represents a full solution to the Schrodinger equation. Remember, the height of that wave, the de Broglie wave, is related to the probability of the particle being in that region. So you can see that if the particle approaches the barrier moving to the right, then there's a high amplitude here indicating that the particle is likely to be on this side, on the left. Then what happens is it encounters the barrier, and that probability will decay exponentially while it's within the barrier. But of course, this exponent never quite reaches 0, and so it emerges on the other side. The amplitude of the particle wave is decreased, but it's non-zero, which means that there is a non-zero probability that the particle can be on that side. Now this is called tunneling, quantum tunneling, or barrier penetration, and the probability that the particle can tunnel through can be described by the transmission coefficient, which we'll call T. And you can look at what the probability is that the particle is reflected as well, and that's the reflection coefficient, R. Now since these both represent probabilities, T plus R sum to 1. So what is T? Well, it's actually a slightly more complicated function than what I show here, but you can approximate T as a decaying exponential. So if you take the limit that kappa times L is much greater than 1, then the transmission probability becomes e to the minus 2 kappa L. And here kappa is described as the square root of 2m times v naught minus e divided by h bar. Remember that m is the mass of the particle, v naught is the barrier height, e is the energy of the particle, and h bar is Planck's constant divided by 2 pi. So if you look at this, if the total mechanical energy of a particle is the kinetic plus the potential energies, then what that means is that while a particle is inside the well, since E is less than the potential energy, that means that your kinetic energy is negative, which seems a little weird. But remember, because of the uncertainty principle, conservation of energy can be violated as long as you don't do it for very long. Okay, so like we said, the transmission coefficient is e to the minus 2 kappa L as long as kappa L is greater than 1. It can be non-zero. The particle can be transmitted or reflected, so if you sum your transmission and reflection coefficients, then that's 1, okay? Now, perhaps we shouldn't be too surprised that this can happen, that quantum tunneling can happen. Remember that both particles and waves display wave-particle duality. So we think of light as a wave. And so we're not too surprised when we have incident light hitting a barrier, and then we have both reflection and transmission of that light, right? But remember, light has wave-particle duality. So in that respect, it's no different from quantum particles, which also display wave-particle duality. Okay? So maybe we shouldn't be surprised that quantum particles can either be tunneled through a barrier or reflect off of a barrier, because it's very similar to light in that way, right? Okay, well, I tried. Quantum mechanics is crazy. It's interesting, and you have to just get used to these ideas. Well, in fact, a beam splitter, pictured here, a common one, is just two triangular prisms secured together, right? And they're secured together with some kind of epoxy, usually. And so you can think of that, a beam splitter for light, as the light tunneling through that barrier of the epoxy or resin or air or whatever holds the barrier in between those two glass, right? And remember that beam splitters, that's what they do. They reflect and transmit light. Okay. An application of quantum tunneling is scanning tunneling microscopy. This is one that's near and dear to my heart, as I'm a microscopist myself. So in STM, or scanning tunneling microscopes, an electrically conducting probe, often tungsten or platinum iridium, is brought near a sample that has to also be electrically conducting. Now the tip is cut so it has a very sharp point, hopefully atomically sharp, but you take what you can get in STM, really. So you bring the tip close to the surface, but not touching the surface, okay? And then what happens is a tunneling current is established because electrons tunnel through from the tip to the sample, and from the sample to the tip, actually. It can go both ways, all right? The empty space in between the tip and the sample represents the barrier that the electrons have to tunnel through, all right? And then the tip and the surface are the two walls of the potential well. So then the electrons tunnel through that barrier. Now, if you just brought the tip close to but not touching the surface and then left it alone, electrons would tunnel in both directions. But what you have to do is apply a bias voltage between the tip and the sample, and then that way there'll be a net tunneling current in one direction. Now in STM, a common mode to run an STM in is called constant current mode. And in that, you choose a tunneling current. Tunneling current values can range from picoamps to nanoamps, for example, to give you an example of the order of magnitude that we're talking about here. But anyway, you choose a set point value for your current, and then you use a feedback loop to maintain that current at a constant value as you scan your tip laterally across the surface. Now, of course, the tunneling current is very sensitive to small changes in that gap, right, in the distance in between the tip and the sample. And so what you have to do is you have to move your tip up and down to maintain that constant current. The amount that you have to move your tip up and down is used to create an image, right, as shown here on the right, okay? So this STM will allow highly detailed images of surfaces with resolutions comparable to the size of a single atom. This image shown here on the right is of a graphite surface, for example. Now, there's a major disadvantage to STM. It is very sensitive to the distance from the tip to the surface, the thickness of the barrier. You have to get your tips really, really super close to the surfaces to get these tunneling currents established. Oftentimes, they're so close and the feedback loop isn't fast enough that you crash your tip into the sample. So that's really common when you do STM. And STM has another serious limitation, and that's that its operation is dependent upon the tip and the sample both being conductive, or a semiconductor. That will work too. And most materials aren't electrically conductive. And that's why atomic force microscopy was born, which doesn't need conductive samples. All right, well, let me do an example problem for you in quantum tunneling. So what's the transmission probability for an electron to tunnel through a 0.5 nanometer gap from a metal to an STM tip if the work function difference between the tip and the sample is 3 electron volts? Okay, so the first step here would be to calculate kappa. And kappa is equal to the square root of 2m times v naught minus e divided by h bar. So I'm plugging in here 2 times the mass of an electron, 9.11 times 10 to the minus 31 kilograms. And the difference, v naught minus e, is the difference in the work functions here, which is 3 electron volts. And then we multiply that times the conversion from joules to EV, 1.602 times 10 to the minus 19 joules per EV. And then we divide by h bar, which is 1.055 times 10 to the minus 34 joules seconds. When we do that, we solve for kappa, and we get 8.87 times 10 to the 9th inverse meters. Now, the transmission coefficient is e to the minus 2 kappa L. So e to the minus 2 times kappa times L, which is 0.5 nanometers, or 0.5 times 10 to the minus 9 meters. And then when you take all that, enter it into your calculator, you get 0.00014, which means that there's a 0.014% chance that the electron will tunnel through, and that'll establish a current. But you can see, due to the low value of this tunneling probability, why the tunneling currents for a scanning tunneling microscope are so small, on the order of picoamps to nanoamps, rather than being large currents. Okay? All right, well, I hope you enjoyed that, and if you have questions, I'll see you in class. Bye-bye.